Good evening. Welcome to the Mind of STEM channel, where you get your daily dose of science, technology, engineering, and math. My name is Leon Jones. In this segment, I'm going to continue with math, because math is very important when you are studying fields like science, medical, accounting, engineering, and even finance. Now, earlier, I did videos on trigonometry, algebra, and calculus. So, tonight, I'm going to get more in depth with calculus. So, I'm going to title this video, What is Vector Calculus? Now, when we talk about vectors, vectors are also part of analytic geometry. And of course, there are also scalars. And when you get into linear algebra, there are eigenvalues and eigenvectors. There's the dot product and the cross product. But now, when we deal with vector calculus, or we call it vector analysis, basically this type of math is concerned with the differentiation and the integration of vector fields, primarily in the three-dimensional sense, or we call it a Euclidean space known as R3. Now, the term vector calculus is sometimes used as a synonym for the broader subject of multivariable calculus, which includes vector calculus as well as partial differentiation and multiple integration. Now, vector calculus plays an important role in differential geometry and in the study of partial differential equations. Why? Because it is extensively used in physics and engineering, especially in the description of electromagnetic fields, gravitational fields, and fluid flow. Now, vector calculus was developed from quaternion analysis by J. Willard Gibbs and Oliver Heaviside near the end of the 19th century, and most of the notation and terminology was established by Gibbs and Edwin Bidwell Wilson in their 1901 book, Vector Analysis. Now, in the conventional form, using cross products, vector calculus does not generalize to higher dimensions, while the alternative approach of geometric algebra uses the exterior products. Now, again, I just mentioned a few of the vector operations, and we're going to enter one right now. Talk about scalar fields. Now, a scalar field associates a scalar value to every point in a space. The scalar is a mathematical number representing a physical quantity. Examples of scalar fields and applications include the temperature distribution throughout space, the pressure distribution in fluid, and a spin-zero quantum fields known as scalar bosons, such as the Higgs field. Now, these fields are the subject of scalar field theory. Then we get into vector fields. A vector field is an assignment of a vector to each point in the space. Now, a vector field in a plane, for instance, can be visualized as a collection of arrows with a given magnitude in a direction attached to a point in the plane. Now, vector fields are often used to model, for example, the speed and direction of a moving fluid throughout space, or the strength and direction of some force, such as the magnetic or gravitational force, as it changes basically from point to point. This can be used, for example, to calculate work done over a line. Now, there are vectors and pseudo-vectors. Now, in the more advanced treatments, one further distinguishes pseudo-vector fields from pseudo-scalar fields, which are identical identical to vector fields and scalar fields, except that they change sign under an orientation reversing map. For example, the curl of a vector is a pseudo-vector field. And if one reflects a vector field, the curl points in the opposite direction. Why? Because the distinction is clarified and elaborated in geometric algebra. Of course, we have vector algebra. Now, the algebraic or non-differential operations in vector calculus are referred to as vector algebra, being defined for a vector space and then globally applied to a vector field. Of course, the basic operations consist of we know as operation. We have vector addition. Vector addition is the addition of two vectors yielding a vector. Scalar multiplication. Multiplication of a scalar and vector yielding a vector. Then I told you about the dot product. Multiplication of two vectors yielding a scalar. Then we have the cross product. Multiplication of two vectors in R3 yielding a pseudo-vector. Then there's vector calculus triple products. The scalar triple product, which is basically the dot product of the cross product of two vectors. Then there's the vector triple product, which is the cross product of the cross product of two vectors. We deal with operators and theorems. Why? Because vector calculus studies various differential operations defined on scalar or vector fields, which are typically expressed in terms of the del operator, also known as the nabla. The three basic vector operators are gradient, which measures the rate and direction of change in a scalar field. And when we deal with the notational analogy, it's multiplication or scale multiplication. And we have a domain and range because maps scalar fields to vector fields. Then we have the divergence, which measures the scalar of a source or sink at a given point in a vector field. Notational analogy is the dot product, maps vector fields to scalar fields. Then there's the curl, measures the tendency to rotate about a point in a vector field in R3. Cross product is the notational analogy, maps vector fields to pseudo-vector fields. And commonly used are two Laplace operators. The Laplacian, which measures the difference between the value of the scalar field with its average on infinitesimal balls, domain and range, maps between scalar fields. Then we have the vector Laplacian, measures the difference between the value of a vector field with its average on infinitesimal balls, domain and range, maps between vector fields. Now, a quantity called the Jacobian matrix is also useful for studying functions when both the domain and range of the function are multivariables, such as a change in variables during integration. And we have the integrational theorems. The three basic vector operations have corresponding theorems which generalize the fundamental theorem of calculus to higher dimensions. There's the gradient theorem, which is the line integral of the gradient of a scalar field over curve L is equal to the change in scalar field between endpoints P and Q of the curve. Then we have the divergence theorem. The integral of a divergence of a vector field over n-dimensional solid V is equal to the flux of the vector field through the n-1 dimensional closed boundary surface of the solid. Then there's the curl, or the Kelvin-Stokes theorem, which is the integral of the curl of a vector field over a surface sigma in R3, or the sum in R3 is basically equal to the circulation of the vector field around the closed curve bounding the surface. And in two dimensions, divergence theorems and curl theorems reduced to the Green's theorem. Again, in two dimensions, the divergence and curl theorems reduced to the Green's theorem. Now, Green's theorem is the integral of the divergence or curl of a vector field over some region A, and R2 equals the flux or circulation of the vector field over the closed curve bounding the region. Now, when we deal with applications, there's linear applications, and linear applications are used to replace complicated functions with linear functions that are almost the same. Given a differentiable function f xy with real values, one can approximate fxy for xy close to AB by the formula. Now, again, when you get into vector calculus, we start talking about linear approximations. Linear approximations also help you determine Simpson's rule and areas under a curve. Now, optimization, you get more into industrial engineering when you get into statistics. Now, for a continuously differential function of several real values at point P, that is a set of values for the input variables, which is viewed as a point in R to the n power, is critical of all partial derivatives of the function are 0 at P, or equivalently, if its gradient is 0, the critical values are the values of the function at critical points. Now, if the function is smooth, or at least twice continuously differentiable, a critical point may either be a local maximum, a local minimum, or even a saddle point. The different cases may be distinguished by considering the eigenvalues of the Hessian matrix of second derivatives. Now, by Fermat's theorem, all local maxima and minima of a differentiable function occur at critical points. Therefore, to find the local maxima and minima, it suffices theoretically to compute the zeros of the gradient and the eigenvalues of the Hessian matrix at these zeros. Now, of course, physics and engineering. Vector calculus is particularly useful in studying the center of mass, field theory, kinetics, and, of course, Maxwell's operations. Now, they're generalizations because vector calculus is initially defined for Euclidean space R3, which has an additional structure beyond simply the three-dimensional real vector space, namely a norm given a notion of length defined via the inner product or the dot product, which in turn gives a notion of an angle and an orientation, which gives a notion of left-handed and right-handed. Why? Because these structures give rise to a volume form and also the cross product, which is used pervasively in vector calculus. Now, the gradient and divergence require only one inner product, while the curl and the cross product requires the handedness of the coordinate system to be taken in an account. Now, vector calculus can also be defined on other three-dimensional real vector spaces if they have an inner product, or more generally, a symmetric, non-degenerate form and orientation. Note that this is less data than an isomorphism to Euclidean space, as it does not require a set of coordinates or a frame of reference, which reflects the fact that vector calculus is invariant under rotations, the special orthogonal group SO3. Now, more generally, vector calculus can be defined by any three-dimensional oriented Riemannian manifold, or more generally, pseudo-Riemannian manifold. Why? Because this structure applies, or this structure simply means that the tangent space at each point has an inner product, more generally a symmetric, non-degenerate form, and an orientation, or more globally, there is a symmetric, non-degenerate metric tensor and an orientation, and works because vector calculus is defined in terms of tangent vectors at each point. How are the dimensions? Most of the analytic results are easy to understand. In a more general form, using machinery of differential geometry, of which vector calculus forms a subset, gradient and divergence generalize immediately to other dimensions, and as do the gradient theorem, divergent theorem, and Laplacian, yielding harmonic analysis, which, while curl and cross product do not generalize as directly. Now, from a general point of view, the various fields, three-dimensional vector calculus, are uniformly seen as being k-sector fields. Scalar fields are zero vector fields. Vector fields are one vector fields. Pseudo-vector fields are two vector fields. And of course, pseudo-scalar fields are three vector fields. In higher dimensions, there are additional types of scalar, vector, pseudo-vector, pseudo-scalar corresponding to 0 over 1 over n minus 1 over n dimensions, which is exhaustive in dimension. So one cannot work with pseudo-scalars and pseudo-vectors. Now, in any dimension, assuming a non-degenerate form, gradient or gradient of a scalar function is basically a vector field. And a divergence of a vector field is a scalar function, but only in dimensions 3 or 7. And trivially, in dimension 0 or 1 is a curl of a vector field only in 3 or 7. Now, dimensions can form a cross product. And again, when they form a cross product, we deal with generalizations, and other dimensionalities either require n-1 vectors to yield one vector, or are alternative Lie algebras, which are more general anti-symmetric bilinear products. Now, the generalization of gradient and divergence and how curl can be generalized is elaborated at curl. Generalizations in brief: the curl of a vector field is a bivector field, which may be interpreted as the special orthogonal Lie algebra of infinitesimal rotations. However, this cannot be identified with a vector field because the dimensions differ. There are 3 dimensions of 3 rotations in 3 dimensions, but 6 dimensions of 4 rotations, and more generally, n2 equals 1/2 n times n-1 dimensions of rotations in n dimensions. Now, there are 2 important alternative generalizations of vector calculus. The first, geometric algebra uses k fields instead of vector fields in 3 or fewer dimensions. Every k value, or let's say every k vector field, can be identified with a scalar function or vector field. But this is not true in higher dimensions. Now, this replaces a cross product, which is specific to 3 dimensions, taking in 2 vector fields and giving as output of a vector field with exterior product, which exists in all dimensions, and takes 2 vector fields, giving as output a bivector, which is a 2 vector field. Now, this product yields Clifford algebras as the algebraic structure on vector spaces with an orientation in non-degenerate form. Now, geometric algebra is mostly used in generalizations of physics and other applied fields of higher dimensions. Now, the second generalization uses differential forms, k covector fields, instead of vector fields or k vector fields, and it is widely used in mathematics, particularly in differential geometry, geometry topology, harmonic analysis, and in particular yielding Hodge theory on oriented pseudo-Riemannian manifolds. Now, from this point of view, grad, curl, and divergence correspond to alternative derivative of 0 forms, 1 forms, and 2 forms respectively, and the key theorems of vector calculus are all special cases of the general form of what we call Stokes' theorem. Now, from the point of view of both of these generalizations, vector calculus implicitly identifies mathematical distinctive objects, which makes the presentation simpler, but the underlying mathematical structure and generalizations less clear. Now, from the point of view of geometric algebra, vector calculus implicitly identifies k vector fields with vector fields or scalar functions, 0 vectors and 3 vectors with scalars, 1 vectors and 2 vectors with vectors. Now, from the point of view of differential forms, vector calculus identifies k forms with scalar fields or vector fields, 0 forms and 3 forms with scalar fields, 1 forms and 2 forms with vector fields. Thus, for example, the curl naturally takes as input a vector field or 1 form, but naturally has a output 2 vector field or form, hence pseudo-vector field, which basically is interpreted as a vector field rather than directly taking a vector field to a vector field. This is reflected in the curl of a vector field in higher dimensions, not having as output a vector field. Now, once again, when we talk about vector calculus or vector analysis, we're basically concerned with differentiation and integration of vector fields primarily in three-dimensional Euclidean space R3. Now that concludes the topic on vector calculus. If you like what I just presented, please comment, share, and subscribe. And if you're looking for some in-depth topics, check out the 401 Talk Zone radio show on YouTube. And you can also check the 401 Talk Zone radio show out on Blog Talk Radio. Now, if you can't find me on YouTube or Blog Talk Radio, you can check me out on Twitter. And once again, I thank you for listening to the Mind of STEM channel, where you get your daily dose of science, technology, engineering, and math. Till next time, my name is Leon Jones. Please have a wonderful and gracious night.